Good morning, good afternoon, and a wonderfully good day po to our panelists, Sir Lester Torres, Sir Vincent Vaso, and to Ma'am Jama Alana Abundo Perez. Our research writing advisor, Sir Gerardo Altamera, our 3 Eyes advisor, Sir Rafael Caisip, our co-researchers of grade 12 STEM age, and to all of the esteemed guests listening to our final defense. We are Research Group STEM Age 1Q, a team of researchers stationed in the FEU Qatar satellite, and on behalf of the whole research group, we would like to greet all of you with an amazing and pleasant day, and thank you for coming to our final research defense. As I mentioned, we will be presenting our final defense comprising of chapters 1 to 5 of our research study entitled Seashell Waste Concrete Hollow Block as an Alternative to Commercial Concrete Hollow Block. Our team of researchers is once again eager to present themselves to you all, so let us get started right away before we formally start. To begin with, I am Charlemagne David.
Hello, I am James Martin J. Binyas.
Hello, my name is Francis Renji Banyaga.
Hello, my name is Nilkar Dayupay.
Good day, my name is Rozan B. Mercado.
Hi, my name is Iana Claire S. Patalinho.
Hi, my name is Regnal Sean C. Princena.
Hi, my name is Mark David T. Quinto.
My name is George Lancelot Tolentino.
Hello, my name is Ritial Cicerine A. Valino.
And without further ado, let us formally begin with the first chapter of our study, the problem and its background.
Our study's background will provide you, as readers, with the context of our study and how and why we're conducting the said research. We focus on addressing the problem of waste management and the increasing cost of construction materials. The researchers have chosen the topic of masonry construction, specifically concrete hollow blocks, which have been widely used for many years. With the aim of creating sustainable materials, we have identified seashells as a potential solution for producing environmentally friendly concrete hollow blocks. While previous studies have explored the use of seashells in concrete production, there is a lack of research on their application, specifically in hollow blocks. Therefore, the study aims to investigate whether seashell waste concrete hollow blocks can serve as a viable substitute for commercial concrete hollow blocks. Thus, as researchers, we have decided to pursue the study entitled Seashell Waste Concrete Hollow Blocks as an alternative to commercial concrete hollow blocks. The theoretical framework will be presented by Ms. Iana.
The building and construction sectors have been striving to adopt environmentally friendly practices to reduce their environmental impact. Consumer interest in sustainable business has grown, and people are increasingly considering the environmental consequences of their choices. The study aligns with the theory of green purchase behavior, which explains how consumers select eco-friendly products based on their past behavior for sustainability. In this context, the researchers utilized recycled seashell waste as a step towards producing eco-friendly materials. Our conceptual framework will be presented by Mr. Charlemagne.
Let us proceed to the conceptual framework. The conceptual framework for the study on seashell waste concrete hollow blocks as an alternative to commercial concrete hollow blocks follows the IPO format, representing input, process, and output. The first is the input. We'll first need the necessary materials that we need in the production of SWCHB or seashell waste concrete hollow block. These materials include fine sand, cement, water, and most importantly, seashell waste. Number 2. We will need a sample of CCHB or commercial concrete hollow block, and this sample will be used later on in the process of the study. Number 3, we will be formulating surveys or form questionnaires that will be assessing the respondents' evaluation of the created product or SWCHB in comparison to the commercialized version or CCHB. The respondents will be evaluating the two in terms of their performance, preferability, and cost. Finally, we will have the profile of the respondents, which includes their age and sex. Proceeding with the process, we start off with the traditional method of the creation of hollow blocks. The method will be used in the production of SWCHB. In the process, we will also test and compare the created product, SWCHB, and the commercial product, or CCHB. We will be taking measurements of both products. We will be measuring their physical characteristics, such as color, texture, weight, drying shrinkage, facial, and web thickness. We will also be measuring both focused on performance like durability, absorption of water, compressive strength, curing duration, and finally, density. Third, we will be giving and getting our respondents' evaluation of SWCHB and CCHB, and finally, we will be getting the statistical analysis and interpretation of the gathered data. Lastly is the output. The output will mainly be on the compiled data gathered through the researchers' assessments and respondents' assessments. The researchers' assessments will be taken from laboratory testings and observations of physical characteristics, product appearance, performance assessments, product effectiveness, and results of statistical analysis. On the other hand, the respondents' assessments will be taken from the results of the surveys or questionnaires from respondents, which will comprise of their evaluations of the hollow block's performance, respondent preferability, and cost preferability. The next to be presented is the statement of the problem and to be presented by Mr. Neil Dayupay.
For our statement of the problem, this study aims to determine if hollow blocks made from various types of seashell waste may be used as an admixture for a low-cost hollow block and alternative for a commercial concrete hollow block, CCHB. The study also seeks to evaluate which type of concrete hollow blocks is the most efficient in terms of product quality, consumer preference, and cost efficiency. Proceeding with the research questions to be started by Ms. Rithiel Valino.
The following research questions were constructed by breaking down the main problem of the study into specific problems. The first research question focuses on the procedures that the researchers followed in gathering and preparing the primary ingredient of the seashell waste concrete hollow block, or SWCHB, which is the seashell waste. The second question refers to the procedures in making the SWCHB and the commercial concrete hollow block, or DCCHB. Third, the researchers seek to know which treatment produced the best outcome by measuring the product's durability, absorption of water, curing duration, and density. Fourth, the researchers also seek to determine the differences and similarities between the physical characteristics of the SWCHB and CCHB in terms of color, texture, weight, drying shrinkage, facial, and web thickness. And to continue, the following research questions will be discussed by Mr. Mark David Quinto.
Fifth, the researchers wish to know which of the two products, SWCHB and CCHB, shows a greater performance in compressive strength, thermal conductivity, and acoustic absorption. Sixth, the researchers seek to know how much does it cost to produce and distribute the SWCHB and CCHB. How much difference does the two have in terms of cost? Seventh, what is the degree of agreement of the respondents on the indicated qualities of SWCHB and CCHB? Qualities that is about performance, preferability, and cost. Eighth, is there a significant difference between the degree of satisfaction of the respondents based on the qualities of hollow blocks with a mixture of seashell waste, or SWCHB, and commercial concrete hollow blocks, CCHB? Moving on to the hypothesis, which would be presented by Mr. George Tolentino.
The research study compares the performance, preferability, and cost of hollow blocks with an admixture of seashell waste to that of a commercial concrete hollow block. The hypothesis suggests that there will be no significant difference between the two types of blocks. Surveys will be conducted among potential users to gather their ratings and opinions. The data analysis will determine if the seashell waste admixture is a viable and cost-effective alternative. Now moving on to the significance of the study presented by Mr. Sean Pincena.
The research study has significant benefits for various groups. It offers concrete hollow block manufacturers new variants for mass production and cost reduction. The construction industry can utilize seashell waste concrete hollow blocks, reducing material costs and enhancing structural performance. The community benefits from waste reduction and prevention of odors and microbial issues. Homeowners can efficiently reuse seashell waste, reducing costs and potentially starting businesses. Future researchers can use this study as a valuable reference for related topics on seashell waste and concrete hollow blocks. The scope and delimitation of our study will be presented by Mr. Adrian. Scope and delimitation. The scope of this study focuses on developing a seashell waste concrete hollow block as a substitute for commercial concrete hollow block.
The study aims to assess products' effectiveness, qualities, and characteristics through laboratory tests, observational tests, and surveys. The laboratory tests will include compressive strength, thermal conductivity, water absorption, and acoustic absorption. Meanwhile, physical characteristics will be attained through observational tests. Furthermore, survey questionnaires will be used to determine the degree of agreement of respondents on performance, preferability, and cost. The delimitation of the study are as follows. The study is limited to the data gathered from the laboratory tests, observational tests, and research surveys conducted by the researchers. The response of the research surveys are limited to 15 males and 15 females residing in Qatar, aged 18 to 60, who are precisely acquainted with testing and evaluating concrete hollow blocks. The research timeline is limited to the first and second semesters of the school year 2022 to 2023.
As we move forward with our studies presentation, let us now shift our focus to the third chapter, which is all about research design and methodology.
The experimental method allowed the researchers to manipulate the independent variable, which is the formulation and production of seashell waste concrete hollow blocks, and examine its effect on the dependent variable, which is the performance of the hollow blocks in the construction industry. The study involved laboratory testing, evaluation by selected respondents, statistical analysis, and comparison of the results. The whole of the study will be presented by James Binyas and Lance Tolentino.
Provided that we are enrolled at Far Eastern University, Roosevelt Rodriguez, the study was conducted in an online setup by offshore students stationed in Qatar and UAE. Specifically, the study was done in the Qatar Satellite Campus.
The seashell waste concrete hollow block or SWCHB were formulated and produced in one of the locations set by the researchers to meet. Residing in Qatar, the researchers used one of the members' houses with an appropriate outdoor space to formulate and produce their desired product at Yasmin Gardens.
To ensure reliable and credible data, the study utilized Doha Technical Laboratories in Qatar for testing the product. DTL is a renowned laboratory in the construction sector, offering a range of testing services for various construction materials. The respondents of the study will be discussed by Mr. Adrian.
Respondents of the study. In this study, the researchers have selected respondents from Qatar who possess knowledge or experience related to the study. The study will involve a total of 30 respondents, 15 males and 15 females, ranging from 18 to 60 years old. The researchers employed purposive and availability sampling techniques in their study. Purposive sampling involves selecting participants based on specific criteria, while availability sampling involves gathering data from readily available individuals. The researchers' instruments will be represented by Ms. Ian.
3 research tools will be used to gather the necessary data for this investigation. The instruments that the researchers will use include an observational assessment or checklist, laboratory testing, and a survey questionnaire. The researchers will carry out an observational assessment, and the assessment will be conducted after the researchers have finished creating the product. The finished product's physical characteristics, such as the product's weight, texture, drying shrinkage, facial, moisture movement, and web thickness will be observed. Following the initial observations, the data will be compared with the physical characteristics of the commercial concrete hollow block. The researchers conducted laboratory testing to gather quantitative data on the performance of seashell waste concrete hollow blocks and commercial concrete hollow blocks. This testing was carried out in a laboratory in Qatar with the assistance of a knowledgeable professional. To gather feedback and evaluations from respondents, survey questionnaires were utilized. The questionnaires were divided into 2 sets, one for each product, which is commercial concrete hollow blocks and seashell waste concrete hollow blocks, allowing the researchers to compare them. The questionnaire consisted of 15 affirmative statements, and respondents indicated their agreement or disagreement on a scale of 1 to 5. This helped determine the respondents' level of agreement with the performance, preferability, and cost of the 2 types of blocks. The data gathering procedure will be presented by Ms. Razan.
To produce seashell waste concrete hollow blocks, the researchers gathered seashell waste, water, fine sand, and cement. Seashells were obtained from beaches or restaurants, while water, sand, and cement were commercially or through natural extraction. The production process involved sterilizing and washing the seashells, powdering them, and mixing them with a dry mixture. The wet and dry mixtures were then combined in a mold to form the hollow blocks, which were cured for 28 days. After curing, the physical characteristics of the seashell waste concrete hollow blocks were observed and compared to the commercially produced concrete hollow blocks. Specific factors such as water absorption, compressive strength, and thermal conductivity require specialized tools and instruments to assess the performance of seashell waste concrete hollow blocks. Therefore, the researchers have identified a laboratory that can provide the necessary equipment and materials for testing. The results obtained from testing the seashell waste concrete hollow blocks were compared to the performance of the commercially produced concrete hollow blocks. Additionally, the researchers distributed the blocks to 30 respondents who evaluated them using a questionnaire measuring cost, preferability, and performance.
Moving on with Chapter 4 is the presentation, analysis, and interpretation of data. Table 1 will be discussed by Ms. Richel.
Table 1 provides the quantity of each component utilized in preparing the seashell waste admixture. The seashell waste were cleaned and sanitized by using distilled water and dishwashing soap, as according to Persetio 2018, seashells must be cleaned with liquid soap to dismiss other microorganisms present within the seashell structure. In total, the study used 7,000 grams of seashell waste, 18,000 grams of water, and 354.88 grams of dishwashing soap for the preparation of the seashell waste admixture. Table 2.1 presents the materials used in the formulation of the SWCHB. The formulation is composed of seashell waste, Portland cement, fine sand, and purified water. As we see from the chart, the quantity of Portland cement, which is 30,000 grams, has the greatest amount. This ingredient is most crucial to ensure the solidity and firmness of the hollow blocks. After a lot of trial and errors, and by maximizing the amount of materials gathered, the researchers were able to formulate a design mix with a ratio of 10:8:7:4, composed of 10 kilograms of Portland cement, 8 kilograms of fine sand, 7 kilograms of seashell waste, and 4 liters of water. 7 kilograms of seashell waste were utilized to achieve the desired product, ensuring its ability to produce a satisfactory performance in the construction industry. The said ratio produced 3 to 4 SWCHBs, and in total, the researchers produced 11 SWCHBs by using the ratio thrice. Table 2.2 provides the information on the formulation used in producing commercial concrete hollow blocks. The formulation is composed of Portland cement, fine sand, coarse aggregate, and purified water. The researchers followed the recommended ratios of the design mix provided by the European Standard for Concrete Masonry Units, specifically for hollow blocks.
The graph shows the compressive strength of seashell waste concrete hollow block and commercial concrete hollow block. It shows that SWCHB has a compressive strength of 3.6 Newton per square millimeter, whereas CCHB has a greater compressive strength with 15.8 Newton per square millimeter. According to MRI concrete block, the compressive strength of concrete blocks is normally in the range of 17.5 Newton per square millimeter or 2,500 pound per square inch. Additionally, the graph shows us the percentage of water absorption of SWCHB and CCHB, which is 6.9% and 5.3% respectively, which meet the standard specifications for concrete hollow blocks. A block with a higher compressive strength is more durable than one with lower compressive strength because it can support more weight, and a block with a low water absorption rate is more durable and will endure longer than a block with a high absorption rate. The graph presents the measured ability of SWCHB and CCHB in water absorption, which refers to the amount of water a concrete hollow block can hold after being soaked. Shown in the graph is the average water absorption of SWCHB, which is 6.9%, and CCHB, which held 5.3%. The test results were obtained through laboratory testing, specifically by administering the test method for full water absorption of concrete masonry units in Doha Technical Laboratories. The first figure illustrates the physical properties of freshly produced concrete hollow blocks without undergoing any curing process. The absence of curing caused the seashell waste concrete hollow blocks to have a darker shade and appear fragile, suggesting a higher moisture content and inadequate evaporation of excess water. Consequently, the second figure depicts the seashell waste concrete hollow blocks after the designated curing duration, indicating the completion of the curing process. The lightened color of the cured seashell waste concrete hollow blocks is due to the controlled moisture evaporation and improved strength and durability. The table presents the measured densities of SWCHB and CCHB. In the context of a hollow block, density refers to the mass or weight of the block per unit volume. Acquiring the density of concrete hollow blocks is crucial as it affects the strength, durability, and insulation properties. Furthermore, according to Lasco, Madlang Bayan, and Sundo, a higher density generally indicates a more significant amount of material within the block, which can result in better structural integrity and resistance to external forces. The first figure showcases the color of seashell waste concrete hollow blocks, which appears dark gray. This coloration indicates the composition ratio employed in the production process, wherein a higher proportion of cement is utilized than sand and other aggregates. The higher cement content contributes to the dark gray hue exhibited by the SWCHB. In contrast, the second figure displays the color of commercialized concrete hollow blocks, which exhibits a lighter shade than SWCHB. This disparity in color suggests a variation in the production ratio, characterized by a lower proportion of cement and a higher ratio of sand and other aggregates. Even a slight alteration in the ratio can result in noticeable differences in the coloration of the produced hollow blocks. The first figure shows a smooth texture of the seashell waste concrete hollow blocks produced using a design mix, indicating a meticulous formation process and a proficient smoothing process. Contrasting the first figure, the other figure depicts the texture exhibited by a concrete hollow block manufactured by a specific company. The visual representation highlights a distinct disparity, revealing a rough texture characterized by the presence of noticeable air pockets and numerous surface fissures. These discernible physical properties observed in CCHB strongly suggest that it was not formed optimally and may have been subjected to external factors, leading to fissures and accumulating air pockets. The graph presents a comparative analysis of seashell waste concrete hollow blocks and commercialized concrete hollow blocks weights. The data reveals that SWCHB generally exhibits lighter weights in comparison to CCHB. Notably, none of the SWCHB samples exceeded 10.30 kilograms, while the weight of the CCHB did not surpass 16.5 kilograms. Moreover, the weight of the CCHB demonstrates a higher level of consistency. The graph also highlights the advantage of SWCHB being lightweight and easily portable compared to the CCHB. This graph represents the data of the observed physical characteristics of the seashell waste concrete hollow blocks and the commercialized concrete hollow blocks in terms of their respective drying shrinkage. The diminution in volume or the size of the hollow blocks that happens during the drying process is referred to as the drying shrinkage. As shown in the graph, the drying shrinkage of the seashell waste concrete hollow blocks is 0.03%. On the other hand, the drying shrinkage of the commercial concrete hollow block is 0.06%, which is higher. This graph showcases the documented measurements of the two products, the seashell waste concrete hollow block and the commercialized concrete hollow blocks. Since the two products are made from two different types of molds, they are expected to differ in measurements. The seashell waste concrete hollow block mold is initially based in the Philippines, with 3 equal cavities. The commercialized concrete hollow blocks are based on the standardized model. This table presents the recorded measurements of the web thickness for two types of blocks, seashell waste concrete hollow blocks and the commercialized concrete hollow blocks. The size of the block's web thickness varies within a range of 0.023 meters to 0.027 meters for SWCHB, while CCHB consistently maintains a web thickness of 0.03 meters across most blocks, although with a few exceptions. Notably, CCHB demonstrates a higher level of uniformity in web thickness measurements compared to SWCHB, where some variations can be observed due to the presence of the three holes or cavities.
Starting with Table 5.1 illustrates the compressive strength of both hollow blocks. Compressive strength is a property that evaluates a material's capacity to sustain applied compressive loads without failing, and is tested using the standard BSEN 772A1. Therefore, an increase in compressive strength would be more acceptable. And according to our data, the CCHB had a compressive strength of 15.8 Newton squared millimeter, while the SWCHB had the compressive strength of 3.6 Newton squared millimeter. Therefore, the commercial concrete hollow blocks demonstrated higher compressive strength when compared to the seashell waste concrete hollow blocks. On the other hand, Table 5.2 depicts the thermal conductivity of both concrete hollow blocks. Thermal conductivity refers to the ability of the concrete hollow blocks to absorb heat with regular exposure to the sun and lights, and is tested using the standard ASTM D5334. A concrete hollow block with a low thermal conductivity would suggest the material would resist heat transfer. With our data, it is apparent that SWCHB exhibited a greater performance in the thermal conductivity of 1.770 watts per meter per degree Kelvin compared to the CCHB of 2.124 watts per meter per degree Kelvin. Lastly, Table 5.3 illustrates the acoustic absorption of the concrete hollow blocks. The hollow block's capacity to decrease or lessen the transmission of sound waves by absorbing some sound energy is known as acoustic absorption. It is measured using BSEN 125044 or the ultrasonic pulse velocity. In the case of a concrete hollow block, high acoustic absorption is desirable. It would suggest that the material can reduce the amount of sound that reflects into a space, thereby reducing the overall noise level and improving the acoustic environment. Evidently, CCHB performed more significantly in terms of acoustic absorption with 1.7 km per second than SWCHB with 1.2 km per second. Our sixth research question focuses on the cost analysis of both SWCHB and CCHB. After analyzing the prices of the components used in each hollow block sample, the cost to produce an SWCHB is significantly lesser than the CCHB, with the SWCHB only paying for the prices of the Portland cement and fine sand, and the CCHB's need for bulk purified water caused the cost difference. The cost difference is 1,010 Qatari riyals. The price to sell an SWCHB is 2 Qatari riyals per hollow block. On the other hand, the CCHB's price is 3 Qatari riyals per hollow blocks. Hence, the SWCHB is more affordable than CCHB. The research questions 7 and 8 will be discussed by Charlie Main.
Table 7.1 illustrates the respondents' degree of agreement on the indicated qualities of SWCHB and CCHB in terms of performance. In the strength category, the results of the evaluation showed that the respondents strongly agreed that the SWCHB didn't break easily while holding, were durable, and didn't immediately crush when dropped from 4 feet, 5 feet, and 6 feet respectively, whilst the respondents only agreed on the CCHB for the same statements. In the resistance category, the results of the evaluation showed that the respondents strongly agreed that the SWCHB did not melt, could withstand its form when exposed to fire, and had lower water absorption. On the other hand, the CCHB's evaluation results from the respondents agreed on the CCHB's ability to not melt and withstand its form when exposed to fire, as well as the water absorption. Table 7.2 illustrates the respondents' degree of agreement on the indicated qualities of SWCHB and CCHB regarding preferability. In the size and weight category, the results of the evaluation showed that the respondents agree that both samples had the standard size for hollow blocks and had the right amount of weight. In the texture category, The results of the evaluation showed that the respondents strongly agreed that the SWCHB had fewer air pockets and fissures, did not leave any product residue, and had a right rough texture, respectively. On the other hand, the CCHB had a collective neutral response from the respondents for the same statements. Lastly, Table 7.3 illustrates the respondents' degree of agreement on the indicated qualities of SWCHB and CCHB regarding cost. In terms of cost, the degree of agreement of the respondents on the indicated qualities of SWCHB and CCHB showed that the respondents strongly agreed that the market price and the production cost of the SWCHB were cheaper to build and was affordable. On the other hand, the results of the evaluation showed that the respondents strongly disagreed that the market price and the production cost of the SWCHB were cheaper to build and affordable. For Table 8.1, after computing the respondents' evaluation results, the computed t-value or t-statistic is 3.60 and thus lie within the rejection region. So, the null hypothesis is rejected. Therefore, there is a significant difference between the degree of satisfaction of the respondents on the indicated qualities of a hollow block with an admixture of seashell waste and a commercial concrete hollow block in terms of their performance. Since the computed cohence D is negative 3.06, there is also a small practical significance of the gathered and computed data regarding the weighted mean score differences between the SWCHB and the CCHB in terms of their performance. For Table 8.2, the null hypothesis is rejected since the computed t-value or test statistic is 4.09 and thus lie within the rejection region. Therefore, there is also a significant difference between the degree of satisfaction of the respondents on the indicated qualities of a hollow block with an admixture of seashell waste and a commercial concrete hollow block in terms of preferability. Since the computed cohence D is negative 2.16, there is also a small practical significance of the gathered and computed data regarding the weighted mean score differences between SWCHB and CCHB in terms of their preferability. Lastly, for Table 8.3, in terms of cost, after computing the respondents' evaluation results, the computed t-value or t-statistic is 92.5 and thus lie within the rejection region. Therefore, the null hypothesis is rejected. Therefore, there is also a significant difference between the degree of satisfaction of the respondents on the indicated qualities of a hollow block with an admixture of seashell waste and a commercial concrete hollow block in terms of cost. Since the computed cohence D is negative 6.36, there is also a small practical significance of the gathered and computed data regarding the weighted mean score differences between the SWCHB and CCHB in terms of their cost.
Our Chapter 5 contains summary and recommendation. Summary will be presented by Mr. Mark.
Our Chapter 5 contains the conclusion and recommendation. So now moving on to the conclusion for each research questions. Research question number 1. The formulation for the preparation of seashell waste mostly involved using water for the soaking and rinsing of the shell, while dishwashing soap was used for thorough cleaning. Research question number 2. SWCHB contained Portland cement as the most abundant component, while CCHB used coarse aggregates. Number 3. CCHB showed better durability with higher compressive strength and lower water absorption. Number 4. SWCHB had a darker color, smoother texture, and lower weight, while CCHB had better drying shrinkage, a more prominent facial, and wider web thickness. Number 5. CCHB performed better in terms of compressive strength, acoustic absorption, while SWCHB had excellent thermal conductivity. Number 6. SWCHB was more cost efficient according to the cost analysis. Number 7. Respondents agreed that both products had the right durability, fire resistance, and size, but they preferred the rough texture and lower cost of SWCHB. And lastly, number 8, the evaluation results rejected the null hypothesis, indicating differences in performance, preference, and cost between SWCHB and CCHB. Now proceeding to the recommendations, which will be presented by Mr. Sean Princena.
Recommendations. The researchers have provided the following recommendations based on their findings. Seashell waste can be utilized by concrete hollow block manufacturers to replace coarse aggregates, reducing production costs and addressing environmental concerns. The construction industry can benefit from incorporating seashell waste, leading to improved thermal conductivity and enhanced performance. Coastal communities are recommended to use seashell waste in block production, contributing to waste reduction and offering business opportunities. Homeowners can consider using seashell waste concrete hollow blocks for better thermal conductivity and affordability. Future researchers should follow its standard ratios, conduct durability tests, and explore properties for accurate grading and data analysis.
Moreover, that ends our study entitled Seashell Waste Concrete Hollow Blocks as an Alternative to Commercial Concrete Hollow Blocks. The researchers are now ready for your comments, suggestions, and constructive criticism for the betterment of this study.